Imagine an extreme Dubai summer afternoon. The heat haze ripples between towering glass facades, and the roads shimmer under blinding sunlight. Inside a modern apartment, a resident feels uncomfortably warm and lowers the thermostat. They wait, but nothing meaningful changes. They lower the temperature again, but the air remains stubbornly warm. This happens because the machinery responsible for cooling this apartment might not be located inside the building. In developed parts of Dubai, cooling is no longer a simple independent appliance. It has been completely transformed into centralized urban infrastructure. Between 12 p.m. and 6 p.m., the city experiences its most intense peak in solar heat absorption and daily electricity demand. This is exactly when enormous district cooling systems must satisfy the thermal load of hundreds of thousands of people simultaneously. If that infrastructure loses its operating margin during a severe stress event, the occupant cannot solve the problem by repairing a small outdoor unit. The true source of the issue could be kilometers away, and the atmospheric variable making this heat rejection difficult is not always the dry temperature you look at on a weather application. To understand why a thermostat can become powerless, you have to follow the cold air backward to its true source. If you move behind the drywall of that apartment and travel below street level, you will not find a traditional outdoor compressor. Instead, you will discover an extensive network of highly insulated underground pipes carrying chilled water. Follow those massive pipes through the subterranean layers of the city, and they will lead you to a sprawling industrial facility known as a district cooling plant. The central plant operates industrial chillers to produce chilled water, and powerful electric pumps push that water through the closed underground distribution network toward connected buildings. Inside the mechanical floor of each building, a localized heat exchanger transfers the collected thermal energy from the indoor air directly into that chilled water. That water, now carrying the accumulated heat of the building, flows back through a parallel return pipe to the central plant to be processed and cooled again. In the Business Bay district alone, specialized district cooling infrastructure actively serves approximately 201 different high-capacity buildings. The fascinating reality is that mechanical cooling has fundamentally transformed into essential urban infrastructure. It functions exactly like the municipal electricity grid or underground telecommunications lines. People use it constantly, every single day, but they rarely see the machinery actually doing the work. But if cold air is delivered through centralized infrastructure, what happens when that exact infrastructure begins running closer to its maximum thermal limits? The answer lies directly in a fundamental contradiction built into the physical laws of air conditioning and thermodynamics. On the left side of this equation is the sprawling modern city itself. Intense summer sunlight impacts thousands of reflective glass facades, and those building surfaces naturally absorb massive amounts of solar radiation. At the exact same time, hundreds of thousands of people enter office buildings, turn on computers, operate commercial restaurant kitchens, and run heavy elevator motors. All of this daily activity generates or absorbs heat, and as a result, the demand for indoor cooling aggressively rises across the entire district. On the right side of the thermal equation is the central district cooling plant. Millions of gallons of warm return water flood back into the facility, carrying all the thermal energy absorbed from those distant buildings. Heavy-duty industrial chillers must forcefully extract that heat. Massive pumps must keep the water circulating, and condenser side systems must receive the extracted thermal energy. Ultimately, the plant cooling towers must successfully reject all that collected heat out into the open outside air. A centralized system does not magically manufacture a comforting substance called cold. It systematically captures and removes heat. The more cooling these connected buildings demand, the more heat the entire infrastructure chain must capture, move, and throw away. The city is not simply asking the central plant to deliver more cold air to its lobbies and living rooms. It is actively sending the plant significantly more heat to deal with. And Dubai's coastal desert atmosphere can make one critical part of that rejection process significantly more demanding than most viewers might expect. When the central plant extracts heat from the returning water loop, it must eventually release that trapped thermal energy directly into the surrounding atmosphere. Many large-scale district cooling facilities rely heavily on towering cooling towers to accomplish this, and these towers reject heat largely through the physical process of evaporation. If you place a wet cloth in front of a rotating fan in a room filled with extremely dry air, the moisture evaporates quickly and the cloth cools down rapidly. But if that same room is already saturated with airborne moisture, that evaporative cooling effect slows down dramatically. This undeniable physical reality introduces a critical meteorological metric known as the wet bulb temperature. The wet bulb temperature matters significantly to engineers because it reflects exactly how much additional evaporative cooling potential the surrounding atmosphere can actually provide. Scorching hot air naturally creates a massive citywide demand for aggressive indoor cooling across the skyline. But exceptionally hot air combined with heavy atmospheric moisture makes the evaporative heat rejection process at the central plant much less favorable. The central machinery simply has to work harder and consume more energy to push the city's collected heat into outside air that is already reluctant to accept moisture. If the cooling towers reject this thermal energy, what exactly is the chemical refrigerant doing inside the plant? The thermal energy from a distant building transfers into the chilled water distribution loop and travels kilometers back to the central chiller unit. Inside the heavy steel casing of that chiller, a specialized chemical refrigerant undergoes a continuous cycle of compression and expansion. The liquid refrigerant absorbs the heavy heat from the incoming water, which lowers the water temperature enough so it can be pumped right back out to the city. The refrigerant then aggressively transfers that absorbed heat over to a completely separate condenser water loop. Finally, the flowing condenser water carries the thermal energy up to the rooftop cooling towers, where it is released into the sky through evaporation. This mechanical chain reveals the absolute reality of the refrigerant illusion. Chemical refrigerant does not destroy heat, and it certainly does not miraculously summon cold air out of nowhere. It simply allows heat to be absorbed from an enclosed indoor space where people do not want it, and pushed toward an outdoor space where it can be safely discarded. Cold is simply the pleasant absence of thermal energy. Massive heat movement is what the heavy machinery is actually doing in the background. Every perfectly comfortable luxury lobby, chilled hotel room, and icy office floor represents a massive volume of heat that had to be physically moved. So what does serious trouble actually look like before a cooling system dramatically fails? Critical urban infrastructure does not become vulnerable only in the exact moment when it completely collapses. It becomes progressively more vulnerable when it slowly loses the operating room for something else to go wrong. As the intense afternoon heat peaks, that available capacity buffer steadily shrinks because additional equipment must work significantly harder just to handle the baseline thermal load. More central chillers activate, secondary pumps push heavy water through the underground network, and cooling tower cells spin up to reject heat into the hot atmosphere. The baseline operating conditions become intensely demanding, and the available reserve margin becomes dangerously smaller. Now imagine one completely ordinary, mundane technical problem occurring under these exact high-stress conditions. It could be a single cooling tower cell suddenly becoming temporarily unavailable, or a condenser water pump developing an electrical fault. On a cool winter morning, the robust central system would easily absorb that minor fault, using its large reserve buffer without anyone noticing. But when the operating margin is already heavily compressed by extreme summer heat, that single isolated equipment fault matters much more. If a standalone machine serving only one small building loses a fraction of its capacity, the resulting problem remains entirely isolated to that specific address. But modern district cooling does not serve just one isolated building. Look again at the sheer scale of the Business Bay district. Highlight one towering glass residential structure, then a massive commercial high-rise, then a luxury hotel, and then dozens of surrounding developments. Inside those sprawling structures, every single interior space is actively generating or absorbing thermal energy. A corner apartment continues taking in heavy solar radiation through its panoramic windows. A critical corporate server room requires absolutely constant temperature control to prevent hardware failure. A massive, bustling retail space actively adds thermal load from thousands of moving shoppers and glowing commercial lighting displays. Every single one of these diverse spaces relies on the exact same underground chilled water network to remain operational. When the centralized cooling plant experiences a rapidly shrinking operating margin, the ordinary occupant standing helplessly at their thermostat has no actual control over the outcome. The digital thermostat on the wall can continuously ask the system for more cooling, but it absolutely cannot manufacture the chilled water feeding the building. Would you rather depend on one highly efficient, centralized cooling network serving an entire urban district, or give every single building its own vulnerable independent cooling system? Because reliable electricity and heavy machinery are not the only things hidden behind Dubai's seemingly infinite supply of cold air. To keep the central industrial chillers operating efficiently under immense pressure, the entire district system requires massive, continuous volumes of water. The outdoor cooling towers reject the city's collected heat, primarily through the process of evaporation, which means pure water is continuously leaving the closed system and vanishing into the hot atmosphere. That lost physical volume must be continuously replaced with fresh makeup water to keep the thermodynamics balanced. The cooling infrastructure requires a dedicated supply line, extensive localized pipe networks, and specialized chemical treatment facilities just to keep the evaporative cooling towers functioning properly. Cooling at this massive municipal scale is not simply one large, independent machine spinning in an isolated basement. It is a deeply interconnected, highly sensitive chain of dependent systems. It strictly requires reliable electricity, continuous makeup water, central chillers, powerful distribution pumps, cooling towers, and an intact underground distribution network to function as a single living entity. If district cooling contains so many moving pieces and complex dependencies, why does Dubai keep building more of it? The undeniable answer is that centralized district cooling provides major, proven efficiency advantages compared to thousands of independent conventional air conditioners straining on separate balconies. A modern central plant can utilize massive industrial chillers, gigantic thermal energy storage tanks, and variable speed equipment that an individual residential apartment building simply cannot afford. Dedicated control rooms constantly monitor the underground network, and specialized maintenance teams ensure the heavy equipment runs at optimal thermodynamic efficiency. The network operator can expand the modular plant precisely as the surrounding district grows, achieving massive economies of scale that save enormous amounts of electrical energy over the long term. The truly disturbing part of this story is not that Dubai chose an obviously bad or fundamentally flawed technology. The centralized system can be incredibly useful and highly efficient. The unsettling part is not that this is a bad engineering idea. It is that a genuinely good idea can become so incredibly useful that an entire modern city starts fundamentally depending on it for basic survival. And Dubai is aggressively connecting more of its expanding footprint to cooling infrastructure exactly like this every single year. Look out across the vast skyline at the heavy construction cranes actively building the next ambitious phase of the city. New residential towers are rapidly rising. New massive underground distribution pipes are being continuously excavated, and new district cooling plants are being engineered. By the first quarter of 2026, the impressive portfolio of the Empower District Cooling Network reached approximately 1,776 connected buildings. These countless buildings do not all precariously depend on one single giant plant, but rather a growing, distributed collection of centralized cooling networks spread across different critical districts. In Business Bay alone, a massive 5th District cooling plant is being meticulously designed to add up to 44,000 refrigeration tons of fresh capacity. Every successful network expansion improves centralized cooling coverage and delivers massive operational electrical efficiency for the city grid. But absolutely every expansion also makes centralized cooling a more deeply embedded, unavoidable part of normal city life. Unprecedented success leads directly to wider adoption. Wider adoption creates deeper systemic dependence, and deeper dependence creates a much higher human consequence if something eventually goes wrong. Dubai's experienced infrastructure engineers did not suddenly forget that the city is located in a harsh, unforgiving desert environment. Modern district cooling plants are specifically overbuilt for extreme hot climate operation. The complex infrastructure is heavily monitored around the clock from advanced control rooms, and dedicated preventive maintenance teams work constantly to protect the sensitive equipment. Central plants are specifically designed with multiple backup chillers, redundant spare capacity, and massive thermal storage tanks to provide a critical safety net during peak hours. They obviously thought about the extreme heat, and they built impressive safeguards to counter it. The real question is, what happens if exceptionally demanding atmospheric weather conditions perfectly coincide with a completely ordinary, localized technical problem? System redundancy can effectively protect an infrastructure network from individual equipment failures. It absolutely cannot repeal the fundamental laws of thermodynamics. To fully understand how a shrinking reserve operating margin actually matters in reality, we have to look closely at a hypothetical engineering stress scenario. This is absolutely not a forecast of an imminent, catastrophic infrastructure disaster, but rather a grounded look at what happens when multiple demanding variables simultaneously align. At exactly 1 p.m., the city of Dubai is intensely hot. The solar thermal load is extremely high, and reflective glass facades across the city are actively absorbing massive amounts of radiant energy. Commercial offices are fully occupied, luxury hotels are highly active, and the network cooling demand rises aggressively. By 2 p.m., significantly more central cooling capacity is actively operating to meet the load. The industrial chillers are moving heat, the distribution pumps are forcefully pushing water, and the massive cooling towers are actively rejecting that thermal energy. By 3 p.m., the entire city is deep inside its broad summer electricity peak period. For this specific hypothetical scenario, assume that local atmospheric conditions are also relatively unfavorable for evaporative heat rejection at the towers. At precisely 3:30 p.m., one entirely ordinary technical problem occurs inside the plant. It only takes a single condenser water pump developing an electrical fault, or one cooling tower cell unexpectedly becoming mechanically unavailable. By 4 p.m., the remaining operational system has significantly less room to accurately compensate for the missing equipment. The available thermal safety margin becomes substantially smaller, and maintaining the strictly desired chilled water temperatures becomes increasingly difficult for the automated systems. If you closely observe the city from the outside, the terrifying version of a Dubai cooling emergency does not necessarily begin with sudden darkness. The street lights could still be perfectly on. The building elevators could still actively move between floors. The skyline could look completely and entirely normal. But the invisible barrier of cold air could begin quietly disappearing. Inside the sealed glass buildings, the physical progression would be entirely silent but deeply uncomfortable. A perfectly comfortable interior lobby gradually becomes slightly warmer as the chilled water loses its optimal temperature. A visiting hotel guest notices the subtle thermal shift and immediately walks over to lower the digital thermostat on the wall. An office worker feels the rising ambient temperature and quietly removes a heavy suit jacket. A busy commercial restaurant kitchen quickly becomes uncomfortably hot, while intense solar heat continues radiating deeply into residential corner apartments. Eventually, frustrated complaints flood into localized building management systems, and daily commercial operations are directly and undeniably affected. If a severe, localized cooling loss continues for a prolonged period under extreme summer heat, it could eventually transition from a mere inconvenience into a serious habitability and health concern. Cooling failure in Dubai is not frightening simply because a heavy machine unexpectedly stops spinning. It is frightening because absolutely normal modern life is built around the strict, unspoken assumption that the mechanical cooling will not fail. At what exact point does air conditioning stop being a simple luxury amenity and permanently become critical urban infrastructure? If you trace the system from the isolated thermostat back through the underground pipes to the central chillers and towering cooling towers, the true nature of the network finally resolves itself. The refrigerant illusion is not the idea that refrigerant will suddenly stop working. Modern chemical refrigerant works incredibly well. The illusion is exactly how humans naturally experience cooling. Inside an enclosed building, it feels exactly as though a machine is magically creating cold air. But physically, the infrastructure is continuously absorbing and aggressively moving massive amounts of heat. Every completely cold lobby represents removed heat. Every comfortably cooled luxury apartment represents removed heat. Every retail space and office floor represents heat that must ultimately go somewhere else. Therefore, Dubai's deeper infrastructure challenge is not simply a question of how much cold the city can actively create. The much more interesting long-term engineering question is how much heat increasingly large centralized cooling networks can continue to move while maintaining enough operating margin for unexpected problems. Dubai has not actually defeated the heat of the desert. It has deliberately engineered underground infrastructure powerful enough to continuously move that heat entirely outside of human experience. When a person walks from brutal outdoor temperatures through a glass door and into a completely cold lobby, that temperature difference exists only because enormous invisible machines are constantly working in the background. The more successful that district infrastructure becomes, the more deeply normal daily life depends upon it continuing to function flawlessly. What happens when cooling stops being comfort and becomes life support for a modern city? This video is an independent engineering and infrastructure analysis created strictly for educational purposes. The scenarios discussed are hypothetical stress models meant to illustrate thermodynamic principles and do not represent a prediction of imminent failure for any specific district cooling network. This content does not constitute professional engineering, architectural, or safety advice. If you found this investigation into Dubai's hidden infrastructure interesting, Leave a comment below with your thoughts on centralized cooling. Subscribe to the channel for more documentaries on how extreme environments constantly test the fundamental limits of modern engineering.